In the second half of this course, we started with regularization and validation. These are two really important concepts for the understanding of machine learning at a theoretical level, but also have very important practical ramifications. First, we looked at regularization. Regularization was the idea about giving up some modeling capability in our extensive models that we might choose from script H to try to gain better performance and lower the problem of variance error. We would add an augmented error term in terms of this omega term over here that would penalize the case where our coefficients attached to our model are too extreme. If we force the coefficients to be a smaller value, they would have less variance on unseen data and probably have less variance error. We can choose a regularizer based on these circumstances. For example, an L1 regularizer that might do some sparse feature pruning or induce feature sparsity, or using an L2 regularizer that would treat all of the different features equally. Commonly, we choose something like weight decay for our omega, such that we emphasize lower weights more. And to decide the amount of regularization that we're going to choose, we could do this by validation. In validation, what we hope to do is bring the training error and the test error as close as possible. We are trying to tune this by holding out some data and trying to estimate its error on testing. However we do that, we can either force this testing data to be close to the true testing data by using as much as possible for training, or try to get the validation error very close to a test data by using lots of data for validation. We can get the best of both worlds by doing cross-validation, in which we rotate the entire data set and cut it up multiple times to try to validate. There's a lot of work in doing this, but it takes additional time to do. When we cross-validate or validate in general, we can manufacture several different data sets. And using these different data sets and training them, we can use a process to choose which set of parameters or which models that we would use is the most useful one that would minimize our validation error, and then choose that for our final set of parameters that we're going to train on an entire data set of size M to yield our final hypothesis that we would pass on in production. After the midterm, we started to look at neural networks. We saw that neural networks are a combination of linear units that allow us to approximate with any number of straight lines any type of curved surface that we want. The whole idea is, again, to use the simple idea of a linear unit, some set of parameters, times the actual observations in our x's, just like the linear perceptron or linear regression. But to push it through a g function, which would be some type of nonlinear activation, which we could then use to compose and stack layers upon layers in order to get more complex boundaries to be engineered as a result. To learn this complex set of weights, we're going to rely on backpropagation, which looks at the loss coming from the very final layer and propagates this backwards from the back of the place, the back of the network where the actual classification is done, all the way to the front of the layer of the network where our inputs are. We do this by analytically considering how the derivative of the loss function changes as we look at how to perturb values that come before and after the particular weight that we're looking at. In week 9, we looked at a very current topic of deep learning, in which deep learning is just an idea of using the neural network architecture and putting it to great use through multiple stacks. The important thing here is that although the topology can be very simple, we needed to make several innovations to make it practical. First, we needed to deal with vanishing gradients. These problems where the gradient gets saturated either too large or too small and causes problems with being able to learn at further regressed layers closer to the input of the stack. Secondly, we needed to be able to pick good initializations for all of the neural network weights before we actually train. We can do that by pre-training using autoencoding. And third, we needed to do some type of regularization and make sure that the neural networks that we create don't overfit to just encode the signal as well as the noise. We do this in part by using dropout. Dropout nullifies parts of our network such that training on different epochs don't rely on the same number of nodes or the same identity nodes to learn the function. At test time, we use all of the nodes in the network. At test time, we use all of the nodes in the network, and we're able to get good performance since none of the nodes are specifically trying to cater for a critical modeling in the algorithm. We saw that there were two basic variants of neural networks in deep learning that we use a lot to regularize towards useful H's. By regularize, we mean to discard a number of weights so as to reduce the number of parameters needed to learn a useful neural network. First one was a recursive neural network, in which we use the same beta parameters, here a matrix of parameters, for multiple time steps in a sequence. Basically, we're sliding the neural network parameters over several consecutive time steps and trying to use all of those time steps using the same neural network parameters to output information or classification at every time step. Secondly, we looked at convolutional neural networks. Again, here the idea is to reuse the same beta, but now instead of for multiple time steps, we're using it for different local regions of an input. For example, in an image or for a set of consecutive words in an input string, if you're talking about natural language processing. Finally, we looked at the idea of transfer learning, which is a hot topic which several of you have used in your team work in your projects. The idea here is to reuse the previously tuned networks for another task. We saw this was embodied by the idea of pre-trained word embeddings, in which Google, Facebook, and other large research centers have engineered very large pre-trained models that somewhat simulates the semantics of words by encoding what words are in its neighbors. In week 10, we looked at ensembles and decision trees. Decision trees themselves are ensembles because they are ensembles of decision stumps, a node at just one layer. All right, a decision stump would take a particular column variable and then recurse it, dividing and conquering it into several different parts. For example, a node that looks at outlook could have three outcomes: sunny, overcast, and rain. And for each of those subproblems, if they are not pure, we could recurse and create a tree-like structure. Now, these decision trees are very expressive. They can easily overfit because each particular instance in our data matrix can be a path through a decision tree that would lead to its particular label, our Y value. For example, if the outlook is sunny and the humidity is less than or equal to 80%, I might decide not to play tennis. In order to combat having each instance be a separate path, we need to prune back the decision tree so that we can combat variance that would be exposed by having different data sets on our function. After looking at decision trees, we looked at two other methods for creating ensembles: bootstrap and bagging, as well as boosting. In bootstrap and bagging, what we wanted to do was create multiple data sets of the same size as the original data set using a bootstrapping technique where we sample with replacement. With each new sample data set, we can train another classifier and take all of these classifiers together and apply uniform voting to get the ensemble decision. By doing this and having multiple data sets, we can cure or address variance in part. Instead of doing bootstrapping, where we randomly pick another data set through sampling with replacement, we could actually make the data sets better by trying to address some of the shortcomings of the previous classification. That was the idea behind boosting. We want to make a strong classifier out of very many simple weak classifiers by reweighting the data set coming from a previous instance to account for harder examples to give more prominence, and lowering the weight of easy examples that could be easily figured out by the original model. We also be able to then lower the bias error because we're using simple hypotheses such as decision slumps as we had used in decision trees in order to make the ensemble. Finally, we put both bootstrap and bagging and boosting together in the idea of a random forest. We took bagging and decision tree learning, as we saw earlier, and tried to produce more randomness through feature projection. The idea that we would take certain features and only project them to a certain tree in the forest, rather than give all of the trees the same features. This would help us to make sure that we would have a large diversity of hypotheses generated, since in decision tree learning, many times the same important node would come out at the top, and without feature projection, random forest fails to work. The bottom line from all of these topics in ensembling is that a diversity of different learners tends to help. In week 11, we looked at unsupervised learning through the idea of k-means and the meta-algorithm of expectation maximization. The key information that we need to know here is the idea that the EM algorithm represents a meta-algorithm where we iteratively estimate two steps. First, an expectation step that assigns data to the model, and then an M step or maximization step where we fit the likelihood of the data to re-estimating the model. And these things are going to recurse back and forth until convergence. We can think of the k-means algorithm, which assigns the classification of points to a cluster to a centroid as a simplified form of the EM algorithm, where the cluster assignments are actually quite hard, right? That means each point belongs to a specific class. And we can do this by using an L2 distance norm. We also looked at the soft GMM method, which is the opposite, in which we use assignments that are soft and using a data likelihood as the norm, as the similarity function in which we're going to use to assign points. We'll finally note that there are many instances of EM out there that you'll find in the literature in machine learning, including forward, backward, and inside out, two algorithms that's very common to see for structured data, like natural language, as well as vision problems. In week 12, we looked at reinforcement learning, the other very important paradigm of learning that wasn't covered earlier. We looked at trying to understand the basic anatomy and terminology in reinforcement learning, including the idea of rewards, actions, and observations. And that Certain reinforcement learning algorithms might have a model of both the agent and the environment, or either one or none. All of this was used to create a policy. The policy here is basically what to do given a certain state. Once a reinforcement learner has a policy, then our job is to try to find the optimal one so that it can make the best decisions given its state. We introduced the idea of the Markov property, which is just to say that all information that we need to make a decision at the next time step, this should be a +1, is encoded in the current time step. Okay, so we don't need all of this information here. We can throw that away and just use the current state to figure out what to do next. We use this to define the Markov chain, which is a series of states and a probability matrix, then a Markov reward process that introduces rewards and some type of exponential decay for future rewards, and then a Markov decision process, where now the state probability matrix is based on a decision made by the agent, and the agent has a selection of different actions it can take. In the post part of this lecture, we also understood the Bellman equations as a recursive form of calculating future rewards. We had two sets of Bellman equations that we looked at. An expectation form, which calculates what's the expected value, and we could see that it has a linear system of equations. The more common ones that we'll see in general in machine learning are the ones for optimal equations. And these are, of course, very important because we'd like to find out the optimal policy, the best policy that an agent should do under the circumstances. We saw this was a nonlinear system due to the fact that we have an operator that's not operating linearly. Finally, in the Bellman equations, we understood the idea of a state value function, both in terms of the state value function as well as the action value function, or Q value. We could see these as interleaved tree of states and actions, in which here we're looking at the Q value that's recursively defined in terms of action values, which happen at the state level, as well as Q values that happen one level beneath. So we can see these interleaved tree of states as being a case of immediate rewards plus discounted future rewards. In our final lecture this week, we looked at ethics. We saw that ethics is a very important consideration that lies outside the mathematical domain of machine learning, but it's very important to consider since a lot of the algorithms that we productionize in machine learning affect real people, inclusive of ourselves. We saw that there are many cases of bias, including reporting bias, automation bias, selection bias, group attribution bias, and implicit bias, and that bias can come in all forms of the data science and machine learning pipeline, from collecting the data, training the model, using the model, having people see the model, and then using the output of how people use the model to create additional training data, and which closes the loop. We need to be sensitive to remove or control for sensitive fields in training and make sure that whatever outcomes that we engineer are fair with respect to the sensitive fields and the outcomes for particular subpopulations that our machine learning systems may be deployed to.